Good evening, everybody. This is Ben Pearson, the Roadster Tracker, and we're going to do something just a little bit different here. The excellent game jam, Ludum Dare, where you develop a game in 48 to 72 hours, depending on which set of rules you use. That's coming up here this weekend, and I kind of sort of want to participate in it. In order to do that, I wanted to get some practice because it's been a little while since I've touched game devs. I've done some fairly extensive stuff over the years, but it's been 3 years since I've done anything real, maybe even longer. I think a little bit longer than that. So we're going to try a rocket simulator, and kind of what I'm envisioning here, and before we really get started with Unity, which will be what we're going to do, let me kind of just draw this out for you. The idea is we have a rocket, and we are launching that off of a planet, and we're trying to get into some kind of an orbit. So we're launching here something like this, and the goal is to get this spacecraft into some desired orbit, which I can't seem to draw, but you know, we'll take this, maybe move it down. Yeah, there we go, something like this, right? So we're trying to go around here. We're going to try to follow the laws of physics reasonably well. So we're going to have a physics engine that has a bunch of different modules that will control different aspects. So one of them is going to be gravity. It will be gravity alone. It will take in the data it needs, and it will output the data. We could have a aerodynamic drag, which so this will be an arrow in, you know, gravity is going to be coming down. Can I rotate this around? So that'll be gravity. The air drag is going to be the opposite of the direction of velocity. We're going to model those as two separate entities entirely, and hopefully that will work reasonably well. What else are we going to do? The air drag, I don't know if we're going to get there. That's low priority. The most important thing, though, is to try to achieve some kind of an orbit, and we're going to take into account inclination. So what we're going to have is, for each rocket, we're going to have some stats here, and it's going to say something like, we want this rocket with the inclination of 50 and a mean or perigee of 200 km, an apogee of 500 km, and the mass is 300 kilograms. We're going to use the same standard rocket for everything. And what we're going to do is kind of automate KSP. So we're going to have some sliders here. So I'm just going to draw some lines here for sliders. And there will be one of these for each stage. So they'll have a couple of different things. I think, so one's going to be the burn time. One will be the gravity turn force. So that'll control this bending. It's how quickly do we want to do that. And then 1 will be the angle. And for starting, and probably all we're going to do for this period of this is these will just be simple sliders, and we may not even actually hard code these into the game. We may have an offline thing because the Unity development GUI is far, far better. But this is kind of our idea. Let's call this Space Launch Simulator. So this is our diagram. Okay. So I'm going to hold this in reference. Eventually we'll need a round body, but we're going to start out with just a simple... We're going to start with a... let's start with a cube. In this cube, we're going to scale it in the... We'll leave the Y dimension alone. For starters, we're just going to see if we can get this rocket off the thing, the pad. And then 0.1. Let's color this, I don't know. We need a material, so let's create a material. That's right, we need that to be here. So we're going to call this ground. And the ground is going to be... let's make it kind of a brownish color. Actually, we'll make it green. Yeah, I like that. So let's drop this material. Okay. Then we have our, first of all, we'll just do a one-stage super simple rocket. So this is called ground. And let's go with a cylinder. Ooh, that's interesting. So we're going to make this quite a bit taller. This one's got to come out of the ground. So we're going to say, I don't know, 10. And then let's make the ground way bigger, actually. Like, way bigger. Okay, where's... Cylinder should not belong to the ground. Ah, that's the problem. So 1, 1, 1, 1, 1, and then we'll make this bigger. Okay. So let's just take a peek at the camera. Let's move our camera up some. Let's move it back. Maybe this direction. There we go. So this is the rocket. Since we're mostly just dinking around, whoops, let's put it like right here as its starting position. So we'll call it 10.5, a little bit off the ground. Okay. Really what we should have done, whoops, let's delete this. The rocket should be this object. So the physics and all can go on here, and this is the rocket, this is the model. So this will have the visual model representing the rocket, which is the collider. We're fine. We may not actually care about that. I don't know. Oops, hang on. Gotta check something real quick. You can see behind the curtain slightly. You can see the curtain. That's what happens when it's not in full screen mode. Okay, and close that. Here we go. Okay, so we have the rocket. Now, I'm okay with this being white for the moment. Let's actually, the model of the rocket, though, I'm going to have it be 0, 0, 0. No. We're going to have it actually be off the ground like this. So we're going to just create a empty object. And this is going to be the particles. So this is just going to be our rocket. So particle system. And we're going to throw off some smoke or something. I don't know. It does not want... Oh, this is the game mode. So let's go to the scene mode. We can zoom out a little bit more. Okay, let's move this straight up just a little bit more. And then the particle renders is here. Well, the first thing we need to do is to give this a material. So let's create a material. There's a lot of options, more than there used to be. So this is going to be particle, rocket, flame, first stage. And then we're just going to make this kind of a bright... Actually, we're going to make it white for now for reasons that are going to become obvious later. So I think they will. We'll find out. Why do we need render mode? None? So we'll do the mesh render mode. And it seems like we need a mesh will be sphere. Let's put in a material. Okay, this is getting better. This material here, we're going to make this a little bit fuzzy. No, let's just do this. We'll do the rest, I think, here. We will tell it to loop. That's fine. Let's see. Gravity modifier. I'm not going to use that. That will be deliberately skipped. The shape of this is going to be a cone. And we want the angle... Can we rotate this like 90 degrees? No, let's try 180. Okay, that's rotating around that axis. Let's try 90. Okay, now it's in the right spot. And just for the fun of this, let's move our rocket higher. Okay. Particle mode, good. I think we want to do an even smaller cone. In fact, let's do like a 2-degree cone. Good. That looks nice. Now we want to have this match the right spot. Good. And then the color. We want to be... Well, we're going to want some randomness. The color over lifetime. So let's check this. And then we can do a gradient here. Let's do a new. So we're going to start out being red, and we're going to end up... Well, we want to start out with a really hot color, like white. And then start out with a cool color like dark red is a pretty good. This one we probably want to be... Actually, we probably want this one to be orange and a darker orange. And then this one to be more of a yellow. Whoops, this one. Okay, this one will be yellow. And then I think we actually even want another thing here. So this one will be white, and then we're going to start off with like a nice bright blue. So that's the color. Why didn't it change that? I don't know. We want this as much as possible to have some randomness. The size over the lifetime. No, we don't want that. Though it does look kind of cool. Trail material? That sounds fun. But I don't think we'll get there. I think we want a lot more of these. We want, and a lot smaller. So we're going to say random between two constants. So it's going to be, say, 3 to 5. The speed start. No, let's have the speed be constant. Start size is going to be random between 2 points. We'll call it 0.1 and 0.2. And we need way, way, way more of these. How do you, the emission rate over time? Wonder why the color is not changing. The color should be it started out as sky blue. See if that changes this. It's really not enough particles, but this will do. This is good enough. This is just a simple rocket simulator, right? Okay, so let's bring this down. Whoopsie daisies, the whole rocket down. And let's check the game mode. Let's hit play and see what happens. Okay, a couple of things. First of all, we need what? Let's say the lifetime is 2 to 3 seconds. The speed is going to be randomly 4 to 5, just to give it a little bit of variety. We probably need a lot more of these if we're going to have a credible effect. Okay, the emission cone, the radius thickness, we're going to have that be like 0.5. And then the angle of cone will be a little bit bigger. Actually, it's like 0.2 even. Let's see how this looks. Nope. Call it a bigger... Oh, we want the angle to be smaller. There we go. That's better. Now, why isn't the color changing? Should we do particles? We're going to do a additive. Let's see how this looks. Ooh. It's getting there. The lifetime is probably a little bit too high. So let's say 1 to 2 seconds lifetime. And then the color. In fact, let's even decrease the lifetime a little bit more. Let's do 0.5 to 1. No, 2. What happens if I do like 20? Apparently I get a crash. Woohoo. Well, that was unexpected. Now you can see all the fun stuff I have on my desktop. I'm not going to send a bug report. Well, let's get back into Unity. Try not to show everything I have on my desktop. Okay. It's probably too many particles. That's probably what happened. Yeah, we'll get there. We didn't hit save at all, so we have the materials, and that is it. Default particle. That's fine. We can create all of this real simple, and then I will hit save immediately after. So this is 0.1, 100 and 100. Gosh, we're learning all sorts of fun stuff to apply. So let's hit save scene. Main. Okay. So this albedo will be... No, we don't want the albedo. We want... Yeah, we do. Just kind of a grassy color, like this. This will do. Okay. So this is our ground. Save the project this time even. How about that? Okay, and we're in game mode. Let's go into scene, and we're going to add in our rocket. Which will be 1, 1, 1. And it's going to have a mesh, a capsule. No, let's not do a capsule. Let's do a cylinder. That cylinder is going to be tall. Let's go with 5 this time. And we're going to put it at 6. So that's its position. So we're going to call this the model. And then we're going to have a particle system. Which already looks better. Color over lifetime will be a gradient that we already have saved. Excellent. And then we need to rotate this like 90 degrees down here. We're going to move the rocket up so we can get a good look at it. And we're going to increase the number of particles and then change the shape to be like, I don't know, 5, and the radius to be 0.2. We're going to move this up right there. And then save. The lifetime we're going to randomize a little bit. It'll be between 1 and 3. Ooh. I don't know. This will do. Okay, so we got our rocket, we got the ground. Let's figure out the physics system. So let's create a folder. And then I'm going to have a interface here. This is going to default be a behavior, but I'm going to call it physics. How do we want to do this? See, this is the kind of things that I got to think about. We want to be able to drag these effects in. We kind of want them to be just inherent. So we'll create we'll call this physics. This is actually going to be an interface. I'm going to use 2017 Visual Studio because that's the version there was when I was last doing this. I'm going to wait to make sure that it loads up reasonable. Okay, good. So this will be an interface. We're going to call this physics. And physics is going to take in... We're going to pass in a data structure. Update state data. So then the question becomes, well, what is state data? Excellent question. So we're going to do a new file. And that file is going to be a C#. Call it a class, but it's really going to be a structure. So what does this structure look like? So we're going to have a vector 3 of pause, vector 3 velocity, vector 3. We're not going to have a acceleration. Or are we? No. Each object is going to apply its acceleration. So this is going to be, what's it called? State data. So can we save as? So this will be an asset. Well, we'll organize this later. State data. Okay. Let's call it a class just for the fun of it. Control-Shift-S. It should have this state data. So the only thing that physics is going to be responsible for is updating the state data, and then I think that's it. So the state data is both the input and the output. It's going to contain the velocity, position, velocity, direction. Now, how do we express the direction? The right way to do this is with a quaternion. Orientation. So that's going to be what direction it's going in. We're going to have, maybe we'll pass in orders. So we're going to create a class order. And order is going to be something similar. It's going to be public no. Okay. Hang on. The order is actually going to be another one of these models. So we don't actually want to pass this in here. But we need to keep track of the state, the orientation. We need float fuel. We need float time. Since the staging. Okay. we need float mass. So mass in kilograms excluding fuel. So the mass should be constant other than staging events. Flow. Mass in kg. I mean, obviously this is not compiling. So we're going to have to figure some stuff out. No. Okay, so we got this. Let's see, using Unity engine. And then quaternion. I probably spelled this wrong. Hey, I got it right. Okay. This should be everything that we need. This will just orbit things around Earth, but I think this is all of the state that we will need. We may do something to make this visible. So these various physics classes are going to get the state data, and they will tweak the... You know what? They all need to operate at the same time. So the resulting thing from here is we need the new... how do we stack these together? So if we have the wind model and we have the gravity model, in reality, they're both happening in the same time. We also need float delta time. How long has it been since we last updated this? Because that's important, because the force will depend. You know, if it's been a second, then you're going to have more of an effect than if it's been 1/100th of a second. So the right thing to do is to return a vector 3 and what it's going to return is the acceleration. How do we manage an orientation change? Actually, I don't think we want to do even that. We can get rid of all of this. This will not depend on Unity directly. Although, because we're using vector 3s and quaternions, then it will. So we're going to do float acceleration. Not float. Vector 3 accel. This is how much this will be multiplied by the delta time. And then the orientation, how do we keep track of that? Let's think this through. I think I'm going to ignore that for now. But in the physics, we are going to have a priority system. And the high priority, the higher the number, the higher we'll update. So then in this case, we do actually want this to be a vector 3. And we're not going to keep track of the acceleration. Yeah, I'm happy with this. Okay, the priority, I mean, it'll have a little bit of an effect, but that's okay. And actually, the priority, we don't even really need this because this is just going to be, they're prioritized by the order that they're added into the system. Okay. So we got this. Let's create another. Let's go back to Unity. We're going to create a script here. Well, let's create a folder here. This is physics, which is a little bit of a loose term, but that's okay. I will put the state data in here. Order, we're going to delete this because we don't need this anymore. What we will have is a mono behavior here that will be here, the physics behavior. And physics behavior is going to take in a list of physics objects. So physics behavior belongs to the rocket. Public physics. I hope that this will let me do this. I can't remember. No. Well, I'll have to look up how to do that, but that's okay. We're going to just say physics equals... Well, before we do that, we need to define the physics. So what will physics look like? Let's create a new file. It's a Visual C# class. And this class is going to be called gravity physics. Implements physics. Extends. How is it that you do this? Oh, it's been too long since I've done a C# extension. I've been working a lot with Java, and they're almost the same. Oh, you just do a colon. Okay. So let's save and see. Gravity physics. We'll just call it gravity, actually. Okay, gravity. It is an interface. So shouldn't it... Well, I would have thought it would have done this already, but that's okay. Vector 3 Excel equals new vector 3. So that will zero it out. And for the purpose here, we're going to do data dot. Actually, we could do this all in one turn. So return data dot position. So this will be its position above from the center of gravity. The position should be ESEF. Earth-centered, Earth. Actually, ESI. Go to definition. So position is going to be Earth-centered, Earth-centered inertial, where ESEF equals ESI at t equals 0. So what does that mean? If we have, let's just create a sphere. We're going to make this way bigger. So let's pretend this sphere is the Earth. Let's call this, we need a material, not lens flare. Create a material. We can put an albedo map. Actually, let's just do like a default checkered, okay? Just to do something. We're going to put that on this. Whoopsie daisies. Why didn't that do a checkered? Just need something with a little bit of texture. A knob. Okay, this will do. So at this one particular position, then ESEF is, so ESEF is defined as the distance from the center of the Earth where the axes will meet, like one will meet at the equator at latitude 0, one will meet at the equator at latitude 90, and one will go through the North Pole. I couldn't tell you exactly what the coordinates are, whoops, but it's something like that. All right. So the ESEF coordinate system rotates with the Earth. The ESI coordinate, ECI coordinate system will rotate with the planet. So, you know, as we're rotating here, then the ESEF coordinate system, as happens here, rotates with it. But the ESI coordinate system, let's do create an empty, whoops, let's create an empty outside of here. So the ESI coordinate system is the true location of things. So if I rotate this, well, it doesn't have the right fixed point, but okay, so here's our globe. The ESI coordinate system, well, let's move this up. And if we rotate, so the game object is rotating, but if we look at the sphere, let's zero out this rotation. It's like if we zero out this rotation, we take the sphere and we rotate it. So this is the ESF. The ESI coordinate system doesn't care. So it's pointing to a different spot than when we rotated the sphere around like this. And that's what the difference is between the two coordinate systems. So we're lining it up at a fixed point in time where the simulation starts, where t equals 0. And then they will have to take into account the Earth's rotation eventually. We're not nearly that far. We just want to have something that launches and has somewhat realistic physics. Another thing, the acceleration profile. So we're really going to have to probably do some kind of a gradient system, which is going to be fun, let me tell you. But for now, this will do. Okay, so let's take our rocket and move it back down to 0. And we have our physics behavior simulator. So in our script, let's pull this open. Physics behavior. So physics equals new physics, new gravity. Okay. We've now defined our physics array. So we have time. So let's see, update time. What's it called? Delta time. Update or fixed update. Is really where this belongs. This is for graphical updates. Fixed update is what we really care about. So Unity engine dot time dot delta time. There we go. This is the time since our last update. Time dot fixed delta time is really the fixed update, what this is being called. So ideally, this fixed update is going to happen periodically. Float dt equals this. So physic for each physics, physic in physics. Okay. too much Java programming, right? Physic.update. And then we need the state data and DT. So the state data, yeah, we gotta get this. Public state data, we're gonna take in float vector 3 pause, vector 3 velocity, quaternion orientation. We'll take in everything. Time, float, mass. Time should be the last thing. So this dot fuel equals fuel. This dot mass equals mass. Time should be last. I thought I said that. Do what I say, not what I do. This dot time equals time. The time will be updated after all of the physics has run. So this is constant in frame. So this is actually static. Not static, constant final. Let's try this. Const. There we go. But it's not constant. It's fixed after we've updated. It's the Java equivalent of final. These two will not. These will not be updated in real time. The fuel can be. So we're going to call this public. We should probably do getters and setters. The position and velocity actually are also only going to be updated. These will only be updated by a tick in frame. Dot position equals pause. This dot velocity equals velocity. This dot orientation equals orientation. So the only things that our physics classes can do, they can have an acceleration that's reported, they can do an orientation change, and that is it. The rest, so public void update, float delta time, vector 3 excel. Then, so velocity will plus equals excel times delta time. And the position plus equals velocity times delta time. Time plus equals delta time. And then the mass is fixed. So that will do. That should update the everything. So then we need to, let's see here. So we need the Excel. vector 3 Excel equals vector 3 dot 0. And then Excel plus equals the physics update, the state data. So let's keep track of the state data. State data. This is actually not public. We don't want that on the outside. So state data, state data. State data equals new state data vector 3 dot 0 vector 3 dot 0 quaternion dot up. I thought there was a way dot angle dot actually, let's have it just be the orientation here. So how do you get the orientation? Transform dot transform dot no, we don't want that. We want the rotation. So transform dot rotation. That'll be in world space, which I think we're okay with. So what else do we need here? We need public int fuel, public, not int float. Float mass. So we're going to call the mass equal to 200 and the fuel equal to 1,000. We'll call the mass equal to 100. Okay. So we have a gravity engine that's just going to pull it straight down. Data.position times we'll have to improve the coordinate system here, because obviously our base coordinate system is like crazy. New vector 3 0 1,000 0. So we're going to pretend that we're 1,000 high, whatever that means. And then data.position. So the gravity will get squared. We're going to call it 9.8 times, this will be a float, times the position squared. Dat.pos times dat.pos divided by 1,000. A billion. So as we get to be higher, then the gravity is going to go down. You actually have to call physics.update. That's weird. Okay. Well, that's fine. We'll just toss this in here. I suppose that will work nicely. Jeez. Gosh, I am that horrible. Dot. Okay. So we do want to be able to get this data. So naming rule violation, yeah, we should probably be more consistent there. But the getter should work, and I don't know why it is not. Upgrade this to 6. Okay, welcome to Unity 6, or C# 6. That was quick. Private set. So the getter will be public. It must be more restrictive than the property. So these are only... So we're going to do public here, so they can be read by the outside world, but they cannot be changed by the outside world. Okay. That I am good with. So you can't multiply a vector by itself, huh? Well, that's interesting. Huh. Well, let's just do this. Pause.x times data.pause.x. And then we're going to do the same thing for y and z. And so then this is going to be x, y, z times new vector 3 x, y, z. Okay. This should do. So this will model the effect of gravity. And then we're going to do another one of these for the engine. And this is going to have the rocket engine will have an inherent mass. I think, well, I'm okay with it. We may have this also be a different component type that has mass, but we're just going to call rocket engine float ISP. That's the key here. So ISP is going to be private. This.isp equals isp. This is not how update is going to work at all. So the only thing we care here is the orientation and the ISP and the thrust. The thrust will actually be the thrust equals thrust. To do thrust will actually be a profile. Eventually that will be the case, but for right now, we're just going to simplify our lives and call it constant. So, what does this actually do? Well, the thrust of a rocket depends on its orientation, and ISP is how much fuel is used, it's its efficiency. The thrust will actually be a profile, which I'm okay with. Thrust equals kilogram, we'll call it newtons of thrust. It's how much acceleration, so it's accel divided by mass equals the acceleration divided by the mass. So we need the total mass of our spacecraft, which will be flow to mass equals data dot fuel plus data dot mass. Data dot fuel minus equals ISP. ISP is defined as the amount of fuel that is burned. Like, if you had a constant thrust that you're trying to produce, it's the amount of fuel. How long can you maintain that fuel with a given amount of fuel? So it's a measurement in seconds. So if you have 200 seconds, then if you have 200 units of fuel, you can maintain the same thrust for 200 seconds. It's a little hard to explain, but this will make sense, we promise here. So we have the ISP time, it'll be the thrust divided by the ISP times delta time. Yeah, I think this will do. It says we don't need these, but I'm okay to leave them in there just to be explicitly clear. So this will handle the thrust, and then we have the actual there's the thrust. Then we already have the mass, so we are good there. The mass is going to be, so it's the thrust divided by mass. That's how much thrust we have, and then we need to figure out the direction. So times data dot orientation dot. So we have the different quaternion terms. We want this to Euler angles. No, we don't want the Euler angles. We want the... Yeah, we do actually want the Euler angles. I think this will do. To do confirm Euler angles. Okay, so the rocket engine will be another behavior here. That was what we called it, didn't we? Gravity and rocket engines. So the rocket engine, we're going to call an ISP of 300, and its thrust will be... So let's think this through. Our rocket weighs... Call it... 11,000 newtons. So we have to be a little bit better than that. So let's call it 13,000 newtons. Why? Quaternion rotation. And then we need the the fuel will be 1,000. Mass will be 100. Time will be 0. Okay. Gravity. We already have the gravity class. Why do we need to have public gravity? No constructor. Nothing. Actually, we'll have the gravitational constant. This will change. We will do an actual realistic if we continue this for that long. But for right now, we're going to say this dot gravity constant equals gravity constant. Beautiful. And so then in our physics behavior class, this actually needs to be 9.8F. Gravity, did I spell gravity right? I don't know why I have two instances of that. Gravity. I don't know. Sometimes weird stuff will... Sometimes this just does weird stuff. Maybe I didn't ever build this in Unity, so it sees it. Okay, let's just see what happens when I hit play. Nothing. It's because we're not actually updating the position any. So we have the acceleration. Then we need to, once we figured out the acceleration, we update the state data. Dot update delta time, and then Excel, and then transform dot position equals state data dot position minus vector 3 0 1000 0. That's our new. removes the base position from this. That's to do better method. Woohoo. We'll get there. Let's run this bad boy. It launched. Oh, so cool. Let's get the camera. Zoom up a little bit. Let's zoom back. And then hit play. So I'm going to click on the rocket so we can see what it looks like. And we can see here that it is getting even faster. It's accelerating pretty clearly. Let's get our camera like way out there. And then let's make our ground at least 10 times bigger. Let's see what this looks like. Hey, how about that? So, save and save the project. I'm actually going to say this is a win for tonight. I may continue this. Let me know what you guys think of this. We will go for trying to do something a little fancier. The next thing is to actually have a proper rounder and not do this flat Earth simulator. Actually, rocket engine. If data.fuel is greater than 0. It's less than 0. We're going to return zeros. So, just for the fun of it, let's set this so we have a lot less fuel. The thrust will be correspondingly sparse, and I'm going to change the ISP so it's worse too. In fact, that's like way worse. Something like this. I want this to run out of fuel. I want to see what happens. Let's way worse ISP. Let's like do 10. Horrible ISP. But it should burn for 10 seconds. Let's see what's happening to the rocket. It's still getting higher. So another to do. We want to thrust if not enough fuel, question mark. Let's just have the ISP be 1. Let's see what this does. Even a steam rocket has better ISP than this. So it should burn out. No. Why not? Let's run this in the debugger. Okay, so data.fuel is 100. So the mass is 200. Now the fuel is very negative. So let's just continue. So the next time, the fuel is 0. So we're returning 0. So we're going to step out of here. I bet you the problem is in gravity. So the gravity needs to be negative. Yeah, that's better. So let's like increase the ISP by a decent amount. Maybe I need to increase the thrust. Let's increase this enough so that we can see that this is the issue. We'll increase the thrust and the ISP both. Probably burning too much fuel. Anyways, I'm going to call this good for now. I may do some debugging and see if we can figure out what's going on between episodes, but I feel a lot better about doing Ludum Dare based off of what I was able to do in an hour and a half and even explain it to you guys. If I'm not explaining it this much, I could have done this in half the time. So, yay. I don't know what we're going to do, but this bodes well. Thanks, guys, for everything. Until next time, keep on tracking. Take care.